All right, welcome back. How's everybody doing? Okay. No, I wish. Okay. So, let me just find everything. Hopefully today's lecture is good and not awful. So today I just want to cover like one last topic. I'm not even sure how long we're going to take on it. Probably the whole class, because that's generally how it works. And then so today is going to be asymptotic analysis. So that's today. And then Monday we'll do an exam review. Slightly good news, I guess. So good news. I've improved the process that I've been using to get exam 2 graded, so I think there is a chance that I will have. I was working on it last night and then I fell asleep. And I worked on it a little bit more today. So hopefully, maybe I can have it done tonight. Maybe tonight. Can I do it tonight? Tonight? Maybe. I've definitely improved the rate of speed because I figured out the best process. The process that I have is if you submitted images, I have images, and I convert them into a PDF. And then I use program, and then I draw over your PDF, and then it's a graded exam. So that's the current process. And if you submitted it as a PDF, that definitely speeds up the process. But I actually found a nice little program here that converts them from images to PDFs in a very user-friendly way that doesn't require too much time. So it's definitely sped up the process. Okay. Let's see if I can. I don't know. All right, let's put this over here. And let's put. Sorry, I'm going to have to move my microphone, so hopefully it doesn't cause too much noise. Okay, there we go. Unfortunately, it was just right in front of the screen, so I couldn't see anything. All right, so that's basically course gibberish. Yeah, and so I'm going to try to get out exam review like a practice. Really what I mean is a practice final. And I'm going to try to get that out. Let's just say tomorrow sometime. Because it depends on what I talk about today and exactly how everything goes. I might throw on a question about big O, big omega, big theta, that kind of stuff. So, okay. So I will say that exam 2 grades have been very good so far, and I've graded probably about 15 of them. And as you see, I had like 4 graded before, and now I've graded 15. And I just need some running time. I need some free time to just kind of blast through them. But I graded like 10 in the course of an hour, so it should take me another few hours. But I think it can, if I just really work on it, I can get it done. I can do, like, the time complexity is now within finite time. Okay. So, all right, let's define big O. So I'm sure some of you have seen big O before. If you're in my 201 class, you saw big O in the previous 2 lectures. So this is kind of going to be a review. Yeah, okay. So we say that f of n, and I'm actually, you can say is. That's what I was saying in 201. Really, I think the best symbol to use here is set inclusion. Can Ben join us today? Everybody loves Ben. I'm sure you guys are going to give me student reviews that say, you know, our actual professor was okay, but why couldn't we have had the other guy? Let me ask him if he wants to join. How do I do that? Good question. Do you want to join for a little big O talk? Oh, incidentally, I should mention this before I go on. Do the reviews for the course. So I just want to say that the department basically came to us with this like safety email that basically said that nothing counts this semester in terms of reviews. Okay, so if you're interested in Ben news, the answer is Ben is resting. He's preparing himself. He might come by later. But do the reviews for the course. The department's basically told us that they won't count against us if they're awful. So really, I think what I want is useful reviews. And what do I mean by useful reviews? Reviews that basically tell me like how different parts of the course went, tell me what you found interesting, tell me what you found hard or easy. Tell me that kind of stuff. Be like, you know, if you spent 2 more days on this topic, or if you spent too much time on this topic, like, you know, that kind of stuff is more useful. If you just say like the course was fine and he was great or terrible, I mean, right? If you say he was the worst professor ever, that doesn't really help me very much. If you say he's the best professor ever, but even that, I mean, I like that much better. I'd much prefer that. But it's still less useful than like a, you know, just tell me as much as you can, because like this is your time to really explain to me like what things were kind of good and bad. And so I do actually, we do read them. I do read them. And I will say that I listen to the useful ones. Yeah, so this is my first semester teaching 203. but not really my first semester teaching math. It's just, this is just a math class of various sorts. Okay. So yeah, I do read reviews, and if it's useful, if there's something I can gain from it, then I try to read them more carefully. If it's yeah. Okay, that's all I want to say about reviews. I know that the response rates are pretty low right now, I think, in general. But I suggest you go and just fill them out. Maybe I'll even offer some extra credit or something for it if you fill it out and send me a screenshot of you don't have to send me a screenshot of the review, but of like you have submitted this review. I don't know, something like that. I'll think about it. Of course, if I say extra credit, everybody's going to say, like, oh my god, I would do anything for that. Okay. So, all right, let's talk about Big O. I wasted 10 minutes on all this class administration. So, if I say f of n is big O of g of n, then what it really means is, and I wrote it in like 203 notation here, but then the point is that I'll explain what I mean by it. It means there exists a c and there exists an n sub 0 such that f of n is less than or equal to c times g of n for n bigger than or equal to n0. So when you read definitions like that, the real answer is like, what the heck does that mean? And so really what you do is you study this part here. We pull this part apart and we look at it and we say, okay, f of n is less than or equal to c times g of n. What does that mean? That means that I can invent a constant, right? There exists a constant. So I get to make this up. I get to pick this. I get to pick the c such that f of n has to be less than or equal to c times g of n. So for instance, if we just do an example, so if I say like 5x squared or 5n squared is big O of n squared, you would say to me, is it or is it not? And the answer is it is, because remember that big O allows us to invent this constant c times n squared. And so what you can always do here is you could just pick this constant to be 6, right? So this constant is going to depend on the function u. Does this have anything to do with the epsilon ball? Oh, don't you wish? You're my 301 student, right? Or one of them. Yes, in Math 301, everything is literally, consider the neighborhood of size epsilon around a point. Everything has to do with that. There's quite a bit of similarity in the definitions, but it's not exactly the same. I'll explain what I mean by that in just a bit. So let's do some other examples of things that are big O of other things. So for instance, if I say n is big O of n squared here, is this true? Well, let's think about it. Is n less than or equal to a constant times n squared? And remember that if we look at the definition, there's something I haven't talked about yet. It's this exists an n0, and it says for n bigger than or equal to n0. So I'll explain what that means in just a bit. For this example, we actually don't really need it, but we need it in a little bit. We can set n0 equal to 1. So basically we just assume that n is bigger than or equal to 1, and n squared is bigger than or equal to 1. And that'll fix some slight issue that we can have with n squareds with powers. So is this true? Well, the answer is probably yes, right? Because if you get to invent c, you can just say that n is less than or equal to a 1 times n squared. Because you know that n, right, is bigger than 1 in general. So if n is bigger than or equal to 1, then 1 is less than or equal to n, therefore n is less than or equal to n squared. And so those are all true statements. And true things makes me happy, so I think that's good. Okay, so yes, it's true that n is big O of n squared. Well, okay, so let's look at, so we know that n is big O of n squared. Is n squared big O of n? And so you notice that I'll use this little in symbol. I think it's one way that you can think of big O of n is as the set of functions f such that f is less than or equal to a constant times g. Such that there exists a c, etc. So that's definitely a legal way to think about it. So if you think about big O of n as all of the functions so that f is less than c times g, then the question is n squared in there, right? Is n squared less than or equal to a constant times n? All right. And so the answer to this is probably not, right? Probably no. And the proof of this is that if you pick any constant c, right? Let's just pick c is equal to, 1,000,000. Then n squared is not always going to be less than 1,000,000 times n. Eventually, if we pick n as, say, 1,000,000 plus 1, then what we're going to see is that 1,000,000 plus 1 squared, oh god, 10 to the 6th plus 1 squared is actually equal to 10 to the 12th plus 2 times 10 to the 6th plus 1, which supposedly is less than equal to 10 to the 6th times 10 to the 6th plus 1, which is equal to 10 to the 12th plus 10 to the 6th. But we see that what we see is that this is going to cancel here, and one of these is going to cancel. And so what we see here, I should just cancel out that 2. The 10 to the 6th stays. Is that this is saying that 1,000,000 plus 1 is less than or equal to 0. And the good news about that is that this is false. Right? So what we know is that if two functions are of different classes or different orders, then n squared is not big O of n. Okay, so let's think about it this way. What about n cubed plus 3n squared minus 2n plus 1? Is that big O of n to the 18th, say? So that's a good question, right? You would say, okay, n cubed plus 3n squared minus 2n plus 1 is less than or equal to some constant times n to the 18th power. And so is that true, right? Is this true? And so the answer that we're going to come to is yes, and what is the reason for that, right? The reason for that is that, if you remember your calculus, right? I mean, one simple thing that we can always do is if we divide both sides by n to the 18th power, and then we take the limit as n goes to infinity of both sides. So the limit over here of the constant c is equal to c. On this side, on the other hand, what is the limit of n cubed over n to the 18th power. I guess really what I should say is like, so n cubed has the best chance, right, of all of these terms to go and at least give you a non-zero limit. So what you see here is that eventually this limit is 0, this limit is c. So is 0 less than or equal to c? And the answer is, yep, pretty sure. So what we see is that big O, it's true that n cubed plus stuff is big O of n to the 18th, but it's also big O of n to the 17th, or say O of n cubed, right? So this one might require a little bit more work. So let's work on that problem. Is it big O of n cubed? And so let's work on the mathematics behind that. So what was it again? Like, it's n cubed minus 3n squared. Actually, it was plus 3n squared minus 2n plus 1. And so we want to bound this less than c times n cubed, where, again, remember that we get to invent this. So the answer is, if you believe that eventually each one of these, so 3n squared, if you believe that n squared is less than n cubed, and I think it's safe to believe that, or if you believe that n is less than n cubed, or 1, for instance, then one thing that you can always do is you can say, oh, well, this is less than or equal to n cubed plus 3n squared. I'm sorry, plus 3n cubed plus, say, 2n. And now you're like, why would you even do this? You don't have to. You can just replace this with 0 if you want, because 0 is bigger than this, plus another n cubed. But we're mathematicians, right? So what we do is we just hammer it with like the most absolutely ridiculous thing we can. And so here what we have is n cubed plus 3n cubed plus either one of these, who cares, plus 0, right? And so if you, let's just say we pick the 0 one, because there's kind of a nice beauty to it, that minus 2n is less than or equal to 0, so that's very nice. Anyway, okay, so if you do this, then what you end up seeing is that we have n cubed plus 3n cubed plus n cubed, so that's what, 5n cubed. But then what you see is that that's actually the exact thing that you need. I think that was the T. That's an L. Whatever. You got to cross your L's and dot your T's. So this 5n cubed is exactly what you need. You get to set the constant c to be 5, and then you're nice and happy. So, okay. Let me show you what all this means graphically. Let me kill off all this stuff. So let's say that we have y is equal to n cubed plus 3n squared minus 2n plus 1. And then let me show you what we have is n cubed. Okay, let me reset the domain here. Okay, what's happening? Oh, right, the y-axis. There we go. Here we are. So if you have these two graphs, you know, what's going to happen here, right? What's going to happen here is that the black graph is the one we care about. this graph is the thing that we're saying it's big O of, but remember that big O says that the first graph, the black graph, has to be less than or equal to it. And it's not, right? You see that here it's always bigger. So that's a slight issue for us. I think the one way to fix it is that we get to multiply it by our constant 5, right? So you notice that the blue equation, well, I'm glad that this is great background noise for you. So we get to multiply it by our little constant. And so this 5, I think we get to do that, right? And so you notice that if we make the constant less and less, eventually it'll start to approach the function. But we know that at least if you pick the constant c equal to 5, you're going to be above the function. And so that's pretty good news. So let's readjust the domain a little bit. Let's adjust the domain to, there we go. And so this isn't really sufficient proof in terms of mathematics, because technically something crazy could go on beyond the range that we see. But because you know that these are polynomials, you know that their end behavior is just kind of going to go pretty much as this goes, right? So this is n cubed. This is the n cubed plus 3n squared minus 2n plus 1. And this thing is 5 times n cubed. So basically, that is big O in a nutshell. Big O is basically just saying that something is an overestimate of the other function, or technically it could be equal to the other function. But I like just calling it a general overestimate. There is the less than or equal to sign. Okay. So here's another one. And we'll talk about programming in just a few minutes, but I just want to talk about, yeah, you could do it the same way. Yeah, I'm just showing you different ways to understand the same thing. So yes, you could divide by n cubed and take the limit, and you would see the same kind of thing where you would, well, I guess instead, right, you would say n cubed plus 2n squared, whatever, plus 0 plus 1, divided by, I guess technically this is a minus 2n or whatever, divided by n cubed. If you put this inside of a limit as n goes to infinity, then what you're going to end up with is, this is going to end up giving you, so these limits with the lower order terms, they all give you 0. And this limit here is not going to give you 0 anymore. It's going to give you 1. But that's okay. Because remember, if I say that something like, is big O of n cubed, that means that, well, what does it mean? It means that that function, right, is less than or equal to the constant times n cubed. And so it's okay if it comes to a finite limit, because that finite limit is going to be the constant c, or something close to the constant c. All right. I want to show this. So first, is this true? I don't know. Let's graph. Here's y equals natural log of n. Here's y equals n. So what do we see that's going on here, right? This is the function, basically f of x equals x, or f of n equals n. So this is, I mean, really this is like the perfect 45-degree function. Right now it's a little less because I think the domain is a little bit messed up. Yeah, there we go. That fixes that. So in computer science, let me just talk about computer science for a second. N normally indicates the number of data elements that you are going to feed into an algorithm. So if you see me kind of taking the domain and shifting over like this to ignore all the negative values, right? You'll understand why I'm doing that. Because if I say, okay, you evaluate this algorithm on -2 things, right? Like we sort a list with -2 elements, or we search a list with -2 elements, or we factor a number with -2 digits. Like most of that is kind of nonsensical. So over here in the region of negative numbers, this is all nonsensical stuff. So we don't have to worry about it. Also, natural log doesn't even exist over there unless you want to take complex analysis. So, yes. But you see that here, I mean, you see n is here. And you see that here, it's clearly just absolutely getting itself murdered by n, right? It's just getting beat pretty badly. So in terms of computer science, though, which is the better thing to have your algorithm run in? So basically, if the x-axis or the n-axis here is the number of data elements that gets fed into an algorithm, the y-axis, right? I can even just write this down maybe. So the n-axis, or you can, x-axis, is the number of data elements. The y-axis, or you might call it the t-axis, is basically the number of steps that the algorithm takes. Yeah, and so you can kind of think of it as runtime. And so clearly, if you have a function like natural log here, and the function is just so much less, right, than this function, then you're gonna want a function that can run faster than a function that goes up higher, because functions that are bigger have higher run times. Functions that are smaller have lower run times. So that is exactly right. Okay, so let's prove. So how should we prove that the natural log of n is less than or equal to n? So basically what I'm trying to say is that the natural log of n is big O of n, but really I'm saying something even more specific. So the natural log of n, and you see it from the graph, right? It's always less than n anyway. So let's just, so at least when n is bigger than 0, so that the natural log exists, etc. But I mean, let's not worry about dimension issues, because remember that n can't really go less than 0, because n is like a number of data sets or data elements that you're sorting or searching. So why is it true that natural log is less? So one way to think about it, if you think about the derivatives, I think someone said, who was it? Nathan, maybe? Someone said, if you take the derivatives of both sides, the derivative on this side is 1 over n, and the derivative on this side is 1. And so as it turns out, because two facts, right? The derivative of this function is always less than the derivative, than this derivative, which is just a constant 1. And natural log of 1 is 0, which means that the natural log of 1 is less than 1. So we know that the function, when you plug in n is equal to 1 into both of these things, this is true for at least that. Another way to do it, you can do it using induction, which was a question on one of my algorithms exams when I was a student. So what you're supposed to do is you say the natural log of 1 is less than 1, because you can assert that the natural, you assert that the natural log of 1 is 0 and this is the base case here. And so that what we're going to do is we're going to say, okay, therefore assume that the natural log of n is less than n. And now we have, and so now what we need to show is that the natural log, and so this is really not the best way to do it. I mean, we can do it this way, but this is definitely not necessarily the best way to do it. The natural log of n plus 1 is less than n plus 1. Is this true, right? We want to know if this is true. So, I don't know. The way I can kind of think of doing this is maybe I'll just say n times I'll run this trick. So this is the trick here. And the trick is that I'm going to factor out n here. When I factor out n, I'm going to get that this natural log is equal to, I mean, so I haven't actually done anything with the log. The log is sitting right here doing nothing. And we still have this inequality, which we don't know is true, but we're going to test it out. The only thing I've done is I've pulled out an n. So when you factor out an n here, you get a 1. When you factor out an n from a 1, remember that 1 is equal to n divided by n. So when you factor out the n, you still have the n in the denominator, but now you also have the n factored out here. And then what am I going to do? Well, I am going to apply a log rule. The log rule I'm going to apply is that the natural log of AB is equal to the natural log of A plus the natural log of B. Yep, you got to apply a log rule here. I'm sorry, guys. So let me just say this will not be on the final. This particular proof is not on the final. I'm not going to make you guys stress out about log rules or anything. But this is just part of the proof, so I'll do it this way. So basically, if we split this apart, then what we're going to get is the natural log of n plus the natural log of 1 plus 1 over n, like this. And then the question is this less than n plus 1? And I'm going to say this is pretty close to done. The only thing we have to do now is basically we're gonna skip over a little bit of the details, I think. But what I will say is that we're going to apply the inductive hypothesis here. The inductive hypothesis already says that the natural log of n is less than n, right? So this part here is already done. This part here is done. So now all I need to show is that the natural log of 1 plus 1 over n is less than 1. So now I need to show this. So of course you might say to yourself, like, ugh, this looks awful, right? But I can just say, there's one thing I can tell myself. I'm just going to rewrite it here. The natural log of 1 plus 1 over n is less than or equal to 1. This is what I want to show. And so the way I'm going to attack it is I'm basically going to invoke the same kind of argument here. I'm just going to say that 1 over n is less than 1. So do you believe this? I do. I believe myself. I do. So if you believe that 1 over n is less than 1, then 1 plus 1 over n is less than 2. Right? So, I mean, I'm not saying anything terrible, I'm not saying anything terribly insightful here. But the trick, the little detail that I'm gonna go over is I'm gonna say the natural log is monotonically increasing. Since the natural log of the derivative no series, I'm going to say natural log is increasing. You can, honestly, you can even just leave out the word monotonically. Yeah, let's actually just leave out the word monotonically. Let's just say natural log is increasing. Better. Since the derivative is positive, so here's all we need to know. The natural log of 2 is approximately 0.693, right? All of you who have that memorized? So because the natural log of 2 is approximately 0.693, here's the good news. It's less than 1, right? And so then we know that this thing here, because we know that 1 plus 1 over n is less than 2, we know that the natural log of 1 plus 1 over n is less than the natural log of 2, which is, again, approximately equal to 0.693, which is less than 1. So we can just draw a giant box on this now, because what we've shown is that the natural log of 1 plus 1 over n is less than 1. And remember, that's what we needed. This is like the technical little stupid bit that we need for this proof, because if you go back, we use the log rule to split this thing up into the natural log of n, which is less than n. And then you have this natural log of this garbage term. And that's the whole point. You have to deal with the garbage. And so the good news is that the garbage is really just less than the natural log of 2. And so given that the garbage is less than natural log of 2, which is, again, approximately 0.693, we know that this is less than 1. So this is true, which completes our whole induction proof, right? This completes the induction proof. Yeah, I mean, I'm not gonna lie and say, like, natural log of 1 plus 1 over n is some great term. I mean, you could always do some horrible thing and, like, look at its Taylor series or something. Like, the natural log of 1 plus 1 over n is equal to, what is it equal to? It's like the sum of, like, minus 1 to the n times 1 over n to the nth power over another n, or I guess over k. Yeah, so we need to make these k's. K equals 0 to infinity, or k equals 1 to infinity. But I was just doing that to troll you guys. Trolled. No Calc 2 here. Okay. So, I think that's all I want to say about Big O in terms of this kind of stuff. I just want to, let's see, yeah, so basically the moral of the story is that the natural log of, this means that natural log of n is Big O of n, which is happy. Okay. So let's look at some algorithms. Yeah. Here's insertion sort. So how many steps does this take? Yeah, so this is done in Python, but it's essentially pseudocode. So yeah, so you have a list, and you're going to insertion sort it using this. So look at what happens here. Here's a for loop. So basically what you do when you're doing big O analysis is that you pretend that the length of the list is equal to n, right? You define this. And so when we define this, what we're doing is we're saying that, okay, this for loop here, right, is going to run from 1 to the length of the list. So it's actually going to run n minus 1 times. But let's just pretend it runs n times, okay? You'll see that it really doesn't matter. So we can say it runs n minus 1 times the number of steps, right, per loop. And so here's the question. How many steps does this internal while loop take, right? What does it do? It starts at I. And so you see j is equal to I. So this is essentially like a for loop that says for j equals I, j is bigger than or equal to 0, j minus minus. You know, if you're into C or C++ for whatever reason. So how many steps does this thing take, right? Well, it takes, unfortunately what it does is it takes I steps. Wow, C++ over Python. Looks like somebody's rooting for punishment. So n minus 1 times, and unfortunately what we're going to have to multiply it by is I steps. And then, of course, how many steps does this take times the step inside the... So what's the step inside y? So swap is going to do some number of things. Let's say that swap does 3 things. And then this j minus equals 1 does 1 thing. And then I don't know if you're going to count this, right? This is a comparison and this is a comparison. So maybe we'll do 2 more things, right? So every time we go through this loop, we're going to do about 5 things. So let's just call it 5. But this I depends on which time we're going through the loop. So actually, if we're going to be really precise, and this is, the good news is we're never going to, in computer science most of the time you're not going to be this precise. You change this into a for loop, or you change this into a summation of, let's see, I is equal to 1 to n. Technically n minus 1, but doesn't matter. And so then we're going to get times 5i, which is equal to 5 times the summation up to n minus 1 of I. And I think you guys have seen this before in this class. I think I talk about this until, you know, everybody's eyes bleed, which is that this is the Gauss sum. So we know that what this is going to be equal to is 5 times n minus 1 divided by 2. Which, as it turns out, it is. Because remember, what this is doing is it's adding up 1 plus 2 plus 3 plus... Oh, you're right. This should be I. There we go. Fixed. Oh, Ben wants in now. Let's see, is he here? He's here. Hello?
Hello.
What's up?
Oh, you know, just watching some cool guy on YouTube be super cool.
I'm talking about insertion sort because we didn't talk about it in 201. It's different, you see.
Oh, it is different.
Yeah.
Wait, I'm supposed to tell you C++ is better than Python? Are you saying that Python's better than C++?
I'm pretending like I'm saying that because technically I'm like the 201 course chair this semester. But
Uh-huh.
honestly, I don't care.
That's the best stance, is I don't care. Yeah.
But we're almost to the punchline of the joke.
Oh.
Or the punchline of the skit or whatever. Which is that this whole mess, right, is simply big O of n squared, right? Because if you evaluate this is 5 halves times n squared minus 5 halves times n. And so we know that big O just respects the top order degree. And so here the top order degree is n squared. Right? Yeep. How do you feel about quicksort, Ben? Oh, you've muted yourself.
I'm sorry. I was dealing with my W's. How do I feel about quicksort? I feel like it's fine. It's no merge sort. Am I right?
Yeah, for some reason I really do prefer merge sort, even though I think quicksort does actually perform better. I think it performs better on like completely randomized lists, though there are apparently ways you can do things to merge sort to actually make it more like quicksort and perform better. But anyway.
Yeah.
So how fast does this run, right?
I mean, it's quicksort, so there's no truth in advertising, so it's probably slow. It's like n to the 4th.
Yeah, that's right. So Ben guesses O of n to the 4th because he's brave. Though I would actually say in a way you're right. So how does quicksort run, right? Let's discuss that for a few minutes. So quicksort is actually, in a way, it's actually a simple sort to think about. What you do is you make yourself 3 lists. Technically, you can do 2, but I don't know. I do 3 now because it simplifies a certain edge case that you can run into where. Anyway, so the point is here. You make 3 lists, and then you go through the list that you're going to sort. And if it's less than the first value in the list, so notice that I call this thing the pivot, which is the list 0, so it's just the first element. So if it's less than the pivot, it goes into the less list. If it's equal to the pivot, it goes into the equal list. And if it's, I approve of Dixon's encouragement of bubble sort because I assume that all the lists are going to be of size less than like 100 or 1,000, so it should be fine. If your list is of size greater than 1,000, then you should probably consider not bubble sort.
Yeah, it's you get also in 201 and 202 we're not concerned with efficiency. That's when you get into our clutches. If you take Eric and I for 341,
that's right.
We get our claws in you and we start making you write efficient code.
Yeah, in a way that is like the point of 341. It's like, okay, remember 201 and 202 where you learned to code? Now do it better.
Yeah, like be good at it now.
Yeah.
Like 201 and 202 is here's how you do it. 341 is like here's how you do it. Well.
Yeah, I mean there are definitely ways to code things that are better. Okay, so anyway, Ben, do you remember the word that I said? My favorite word that like quicksort. If I wanted to describe quicksort to a mathematician, I would just say this one word. Which is
tracheectomy?
Yeah, tracheotomy.
No, tracheectomy. It's when you remove the trachea.
Thank you, Ben. You know why I like you, Ben?
Why?
Because you are the most useful sidekick of all the comments that you could give. It's always the most on point.
Oh, I'm the Andy Richter to your Conan O'Brien.
That's a good reference because I definitely still have some love for Conan O'Brien.
Yeah.
So trichotomy. So all trichotomy means is it's a fancy word that was invented that's saying if you have a number, right, that number is all numbers are either less than that number, equal to that number, or greater than that number. And you're like, and you think to yourself, like, wowzers, right? Like that's just absolutely the most insane thing I've ever heard. And as it turns out, it's not. So, but it has a name. Wowzer. All right. So basically the idea is you divide the list in thirds. We'll pretend that a third of the stuff goes into the less list, a third of the stuff goes into the equal list, and a third of the stuff goes into the greater list. Or maybe we can even pretend that half goes into the HALF, because English is not phonetic. HALF. And we'll just pretend that maybe one thing goes into the equal list. Though, of course, this can vary. But then what happens is this is a recursive function that returns a quicksort on the less list, it returns a quicksort on the greater list, and then it returns just the equal list. So it adds them all together in the end. So here's a question. How many steps does this thing go, right? And the answer is, well, what happens, right? Let's think about it. So let's pretend like it's dividing the list in half each time, right? So what it's doing is it's saying, let's pick a pivot. And then here's the less list. Here's the equal list. Let's draw it smaller. And here's the greater list.
It's biggies and smallies, right?
Yeah. And so this is of size approximately n divided by 2. This is of size approximately n divided by 2. And this is of size approximately 1, right? I'm not saying it's the only thing in here. It could be 2 or 3, but let's just assume it's approximately 1. So then what you have to do is you have to sort this one. And the less list is going to break into two lists of size n divided by 4. And now this is an approximation, right? This is like a best case scenario for this algorithm. It could accidentally be that you pick the wrong pivot and everything goes into the greater list or into the less list. But we're just assuming here that that doesn't happen, right? We're assuming best case perfect division kind of scenarios. Okay, cool. So then this one divides into two lists of size approximately n over 8. Here's the equal list of approximately size 1. And here's another list of size n over 8. And the same thing happens for all of these. Same. So how do we know when to stop, right? So if we look at the code basically tells us when to stop, right? The code says, well, if I hadn't overwritten it with a big circle. So if the length of the list is bigger than or equal to 2, then do all this stuff. Else just return the list, right? So when the list size is less than 2, it's just going to, instead of doing this, right, it's just going to give us back the original list. So eventually, right, n divided by something is less than or equal to 2, right? I guess actually just strictly less than 2, meaning either 0 or 1. So let's say that n divided by something is equal to 2. Or, I'm sorry, equal to 1. That means that n is, now of course this is technically like rounding down, I guess. So what it really means is that n is approximately equal to something. But what do we notice about these somethings, right? This one is 2. Then at the next level we divide by 4. Then at the next level we divide by 8. And at the next level we'll divide by what? We're going to divide by 16, then 32, then 64.
Oh, I noticed a pattern.
Oh, did you now?
Yeah, they're all positive numbers.
Very good.
Nice.
Well, there's something a little bit more computer sciencey about the numbers 2, 4, 8, 16, 32, 64, 128, etc.
Oh, they're integers?
Nah. They are powers of 2.
Oh.
And so what we can say is that eventually what's going to happen is that we know that n is approximately 2 to the p. So, of course, now we have to use the thing that we love.
Everyone loves it.
We have to hit this thing with a log. So we'll get the log of n is equal to p. And remember, or I'm going to say recall, which means I'm teaching this for the first time, that lg of x is equal to log base 2. Oh, did you like that?
It's a good...
That's the mathematician's trick. I remember I was taking a class on algebra in grad school, and the professor was like, recall the fundamental theorem of finite abelian groups that you learned in elementary school. I kid you not, he said those exact words. You know, so that's how you usually get talked to.
Hey, Eric.
Hey, what?
Hey.
I'm here. What do you want?
Should I do the joke again? I should do the joke again.
What's the joke?
So, well, this is the class. Guys. You know this is DJE, right? That you're talking. Your professor, like we covered this a while back. That your professor is a DJ, and whenever he writes LG of X, right? Whenever he writes that, what is he doing? He's not writing that 2 at the bottom, which means you could say he's dropping the bass. Boom, 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 boom.
Okay, I'm gonna mute you now.
It's been a long semester. I'm reusing my jokes.
Oh, it's all right. That's the one thing about teaching is that you get to reuse your jokes every semester, but this one is reused from like 2 days ago.
I know. I like Joby. I've never seen them like write a comment until now. It's a good premiere. I agree.
Yep.
But that's what DJE does. He drops the bass.
Okay. Well, anyway. So this is actually a fun one. Because each one of these things takes however long, so this whole step takes n to run. And then this whole step here takes n to run because we're basically scanning over 4 lists of size 4. And then at this step we're scanning over 8 lists of size 8. Or I'm not of size 8, of n divided by 8. There we go. 4 lists of size n divided by 4. Here is 2 lists of size n divided by 2. And of course, I should be more precise about this by saying like, oh, it's actually technically maybe the ceiling of the blah blah blah, but I don't care. We don't have to be that technical. And so what we're doing here, and then what you notice is that it takes lgn steps, which is the log of n steps, base 2. And so each step takes n total time to run, and we're running lg of n steps, which means... Thank you. That the overall runtime for this algorithm, and I'm just going to say, it is going to be approximately, at least in the best case...
n squared.
No. N times the lg of n. And just remember that this is the best case for this algorithm. This is not the worst case. Right? I've only defined big O in this class, so that's all.
Oh, you zoomed in. That was impactful.
I know. Best case. So, yes, I think this is actually a pretty good place to stop in terms of this material And maybe you'd be interested in the birthday problem, Ben.
Oh, the birthday paradox
Yeah.
with the pigeonhole principle.
Well, it's sort of the pigeonhole principle, but yeah.
But we're not going to talk about how it's actually worst case n squared.
No, I don't care about that.
Oh no! All right.
Well, like, look, they're going to talk about that in 341, right?
Are
Like,
they? I
what?
didn't talk about it in 341.
No?
No, I didn't go over sorting yet.
Okay.
There's a fire truck going by.
I know, I
No, I
like
didn't
how
go
every
sorting
time you
those.
actually speak, the fire truck comes through, and every time you're quiet, your compressor is like, oh, it's below the threshold, so it just smashes you to 0. So it's like every time you speak, it's like, "Ree, hello."
I did amortized analysis today and blew their minds. There was the one student said that they were having trouble coping with the amount of reality that just got exploded on them with amortized
Yeah,
analysis.
you know what? I will just say the worst case of this algorithm is O of n squared. By the way, there is some bad stuff that can happen. But since this is not an algorithms class, and this is not a data structures class, and this is not 201 or 202, I'm not actually really covering that. What I'm covering is more of the mathematics behind Big O.
Yeah.
But
The interesting thing about the worst case, though, for quicksort is that it's on a sorted list. If the list is already sorted, you get the worst case performance.
That's right. Because what ends up
Which is
happening,
funny because bubble sort is that's its best case. So.
Yep. Okay.
What happens is the pivot always it makes it so that the first thing is equal and then everything's greater than it, so you actually end up
so everything goes into the greater list here, which means that actually what you have is something closer to 1, 1, n, like that, which is the worst case scenario, because then you're basically peeling off, or 1, 1, say n minus 1 or something like that.
It's 0, 1.
Yeah, 0, 1,
minus
n
1,
minus, if we're being really exact. Yeah, sorted in reverse order is also an equivalent.
Equivalently bad, yes.
Was I saying the word right? What was I saying?
I don't know.
Anyway.
I don't know. I thought you might be like turning into a dragon or something. So I was just gonna let it happen.
Equivalently bad. Yeah, equally bad. Oh, I could have just said equally, but I didn't say that.
Yeah, I'm sure it's like more precise for like something.
So here's the last new thing for the course, because we're just going to be doing exam review on Monday. Here's the birthday problem. How many people?
Like a good one.
How many people do you need to ensure that the proper? How many people in a room do you need to ensure that the probability of a duplicate birthday is higher than, say, 50%, or maybe 75%, or maybe 90%? Who cares? Some percentage p.
I have a follow-up question.
Fine.
Are we at the Iron Age in Ellicott City? Because that really.
No.
Like, are people? We're not. Okay, because that.
Why? Because it was Oh yeah, I remember that. Literally, it was everybody's birthday there. I guess
then you would just need 2 people.
Yeah, the probability of that would be like, well, how would you rate that as a percent? Yeah. Anyway, yeah, it's just like, Jesus, it really is terrible.
Iron Age, now that we can't go there, but it is pretty good. But that also, if you go on a busy night, there will be no less than 11 birthdays. I'm not joking. All right, let's do it. Tell me about it. Give me your probabilities.
So here's the fun part about it.
Is this really low, actually?
Well, don't spoil the fun, man.
But it's surprisingly low. It's lower than they even probably think.
Stop spoiling the fun.
It's 2. The answer is 2.
Oh my god. I'm
sorry.
I might have to murder you. But that's okay.
No.
We're in quarantine. I can't even. We have to socially distance murder. Okay. So, okay. Here's the idea. What we want to do is we want to ask an equivalent question. What is the probability? What is the P? Or prob that if we have n people, no one shares a birthday. And so the way to do this is, well, if you have one person, they have 365 choices for their birthday, right? Because they know that they're never going to share with anyone else. I mean, technically they only have one choice because it's their birthday, but let's pretend that, like, we're allowed to pick amongst all the people in the universe to shove in a room, right? So we have 365 days. So this is person one.
And we have that power, and we're going to use it for this problem.
Well, I mean, we're mathematicians. This is the kind of stuff we do, right? Well, like, we always put people into groups, and we're like, we know that either in a group of 6 people, that either 3 people are all friends, or there are at least 3 mutually non-friends, right? I mean, like, that's the stuff we say. So, what about the next person? So this is person 1. For person 2, remember, no one is sharing a birthday. So how many choices do we have, Mr. Benj1? Oh God! And no leap years. All people with leap year birthdays are excluded from the universe.
364.
That's right. And then, let's say that we're going to throw a third person in the room. We get 363, right? Over 365. And, like, maybe a fourth person, 362 over 365. Do we sense a pattern here, right? So this is the probability that 4 people don't share a birthday, right?
Oh, you know what? This is, the numbers are doubling each time. These are powers of 2.
You know, Ben, useful as always. So, basically, this is equal to big pi from I equals 0.
God, that pi has such a good haircut.
Uh-huh.
Man.
There we go. Now it's a little less ostentatious.
Oh, no! What are you? Oh. Literally unplayable.
It's the product of all this stuff, right? So, so this is the probability that no one shares. So how do we get the probability that someone shares? Right? What we do...
We subtract that from 1.
Yep.
There we go.
So
it's got little, like, claw arms.
Yeah. Cool.
How do I solve this product, Eric?
I have no idea.
No?
Like, literally, I'm lost. I couldn't say. So what I'm going to do is I am going to code it up. Yeah, I'm lazy. So what I'm going to do, here we are. I'm going to make a new Python file.
I love for a mathematician, it's like, oh, I'm feeling lazy. I'm going to code it up.
So here we go. Well, I mean, so there are ways to think about it. You could use the Stirling approximation to get an approximation of the factorial. Look. There's paths, right? But here's what we're gonna do. Here we go. Birthdays of n. We're gonna say the prob equals 1, and then we're gonna say for I in range, and we're gonna say n, and then we're gonna multiply prob times equals 365 minus I divided by 365. Cool. So, And then I guess we can return, what you call it? Prob.
1 minus that.
Oh yeah, we can return 1 minus prob and be even happier. So
Incredible happiness.
yeah, and so there we go. Yes, you do. We're in the exam 2 grading folder, in fact. So why don't we just do this? Oh yeah, so it's running tests on my own code. So don't worry about this. This is not running tests on your code. This is testing my own code. So for n,
not. It's 201, right?
Yeah, but some of these kids are into my 201 class.
Oh, sure.
And by kids, I mean amazing humans.
Yeah, of course. Everybody's kids. He talks about his parents that way. I'm not lying.
I think
I'll ask him about the kids, and he first will be like, "Do you mean the students or my parents?"
Oh, birthdays. All right, let's do it. What do you say? What do you think? What do you know?
Well, what about 366?
I don't believe in 366.
But then it won't do 365.
I don't care.
Oh, wow, you're a monster.
All right, fine. You win. So the first question is this going to work? The answer is, who the heck knows? You say no? I say possibly.
Because it's not lacking confidence in you. It's just that I always expect that code won't work. After years of doing software development, I know the go button is going to be an error. Oh my gosh.
Look at that.
It doesn't work. Oh wait, there it does.
Yeah, it did. Shut up. So
it's just a rounding error. Okay.
Okay, here's what we go. So if we have 2 people, there's a 0.2% chance that they share the birthday, which I think is approximately just 1 over 365, right?
Mm-hmm.
Yeah, 1 over 365 is that number, which you see matches. So that's fine. Ain't nothing wrong with that.
Ain't nothing wrong with that.
If you have 3 people in a room, there's a 0.8% chance, right? You know what we could do? We could multiply these numbers by 100 and smash that like button again.
Smash that like button. Come on, guys.
So now it's actually in percentages. So you see that here it goes up from 1%, 2%, 4%, 5%. So it's actually going up a little faster than just linearly, right? And then here it starts to kind of kick itself up into high gear. So as it turns out, yes, we have 24 current viewers according to the YouTubes. So as it turns out, there's actually there's a 53.8% chance that someone in here shares a birthday.
When's your birthday, Eric?
November the 14th.
I knew that, actually. Mine's October the 14th. We're a month apart.
We're literally a month apart. We're a year
year.
We're a year and a month apart, but that's fine.
Or are we 11 months apart?
No, we're a year and a month.
No, it's a year and a month.
We're a year and a month. Because technically, yeah. So cool.
But there's a half chance somebody watching. Well, and if we add no, I'm a watcher, so it's just you. So
yeah,
we're actually 25.
I think I might actually be watching too, or am I watching? I don't know. So anyway, so yeah, we have 24 people, 25 people, somewhere in there. I know we saw 25 for just a second, but then that person immediately left because they hate us.
Because they saw numbers.
They were like,
where have I? Whoa, I've gone to the wrong part of YouTube. I just wanted to watch cat and cake decorating videos.
But you see, this is the really cool part, is that you notice that actually if we had 30 people in here, there would be a 70% chance, right? And so that increased way faster than linearly, right? And as it turns out, if you scroll down just a little bit, let's say that we had all 80 people from this class in there, there'd be a 99.99% chance that if we had everybody for the class at the same time looking at this stream, there would be a 1 in 100,000 chance, essentially, that we didn't have a match. That's pretty good, right? That's something
Yeah.
you'd bet $100 on. Probably bet $10,000 on it or something like that, given the expected value of success. So,
Yeah.
yeah, it's a pretty good bet.
Yeah.
So, yeah. So actually, I think the birthday problem is pretty cool, and it's like it's a nice little bookend to the course, right? It makes you feel like, oh look, math can be cute.
Yeah.
And also, look at how we programmed in the solution because we didn't feel like doing the actual like approximations that maybe you would do if you were like a true Eulerian kind of, you were blind and you had to do math that way. Anyway,
Mm-hmm.
good old Euler,
Mm-hmm.
Apparently, when he lost sight in his right eye, he said, "Ah, good, fewer distractions."
You math people are some kind of people.
So, all right. Thus ends 203, except for the review section. All the material has been covered. I feel like I've covered more material than I had to. I've punished you more than was required.
Or you gifted them
But
with
I
the
did
knowledge.
2 days of like, I shouldn't even call it baby graph theory because it wasn't really baby graph theory. It was just kind of like gentle graph theory. It was like advanced graph theory, but I didn't do a whole lot of proofs and didn't do a lot of the really technical stuff. So it's all the really cool stuff about it.
Now we get to see these lovely nerds back in the fall.
I know if they
341.
take our 341 sections, then they are lucky enough to hopefully
Yeah.
we'll get to see them in person,
I hope so too.
and
I
then
hope so too.
I'll be like, I remember you people. I know who
wonder
you
if
are.
I hope I don't conflict with your time so we can like double up on our like board games and stuff like that. It's fun.
I think it's possible.
Patrick,
Why?
you're a mod because you watch the 201 lectures on
Yeah,
here.
you're a mod on my channel, and so you are a mod on in 201.
Woo.
Man, poor Juliana. Had her in 201, had her in 203, now in 341.
Getting the full Eric rundown. You should try to teach algorithms next spring. And
Good
Juliana
God,
can
wouldn't
just
that
have,
be
like,
wouldn't that be like the worst possible universe? Like,
pretty bad.
like
You should
Leibniz,
get some sort of like special award.
like
for-
Leibniz and what's his name? What's that guy who wrote that book? Crap.
Michael Crichton.
No. About the best of all possible worlds.
Pangloss.
Yes. Where is
Pangloss
what book
is
is?
a character.
Yeah, he's a character. Who wrote the book? Voltaire.
That's right. I was
Voltaire
about to say, he was a French
wrote
guy.
Candide,
That's right.
in which Pangloss is a character.
Yes.
Voltaire, of course, referencing the Leibnizian philosophy of the fact that, mocking the idea that we could be living in the best of all possible universes.
Yeah. It was also isn't the thesis for that thing is to cultivate your garden. So that's what you guys have to do this summer. Is go cultivate your gardens. Whatever your garden is, if your garden is playing the oh my gosh, I can't remember the name, the instrument that you play, but with theremin. If theremin brings you true fulfillment, go cultivate that garden. Or I don't know, dog walking, or I don't know, scuba diving. Cultivate your gardens.
Yeah, my hope is that you guys spend this summer finding something and actually enjoying it.
Yeah.
Whatever it is.
Yeah.
Because now is in a way, we have all dreamt, as bad as all the corona stuff is, right? We've all, in a sense, dreamt of having infinite time, infinite with a asterisk over it, to do whatever it is that we want to do, right? For a certain hobby, for a certain intellectual pursuit, for whatever it is. I mean, I've dreamt of it. I'm sure you've dreamt of it, Ben. If I had the time, right, I would do X.
Yeah. I mean, I'm pretty sure I'm gonna take a big nap. That's my dream.
You know, honestly, I've been doing a lot more of that this semester. I've been sleeping so well. It's last semester I slept maybe 1 or 2 nights a week. Now I've been sleeping almost every night. I don't even know
Wow.
what's wrong with me.
Wow.
I think I'm just getting
I
older,
sleep
Ben.
sleep is my me time. I always make sure I get my sleep in.
Yeah.
I love sleeping.
The one thing I will say about the 203 final is that I think I'm just gonna write it straight up in the sense that I don't think it's gonna be that hard. It's not gonna be like exam two. Exam two was kind of my pet exam. Um, so there was an email that was sent out by Hrabowski about online classes in the fall. The good news is that we're just, I think, exercising extreme vagueness, and the reason why we're exercising that vagueness is because no one really knows. Oh, of course, Ben. Yes.
Opnig, not hoping. I don't know what's been with my eye key, but my eyes do not want to go into the right spots in words. They just keep jumping around. Sometimes they duplicate.
Well, you see, my students are completely fine with this because we have talked so much about distinguishable permutations that
Hopnig sounds like some sort of like German philosopher.
yeah.
That might have been buddies with Leibniz or something.
I mean, it sounds a little bit like Hopf.
Or Kopf.
Yeah, but there's
I
something
like hunting.
there's a thing in the mathematics that's called the Hopf vibration.
What's your favorite English language accent? Do you have a favorite? And also, why is it Baltimore?
I mean, I will say, I do enjoy mocking, but I don't know if I'll say. But what's my favorite accent? That's a good question.
Duras. Honda Civic. I like New Zealand and Ireland.
So I've been watching a lot of the Hydraulic Press channel lately, and it's a Finnish guy who runs that channel, and I do like the Finnish accent in English. I think I think apparently they have a phrase for it. They call it rally English. I don't know.
Okay. I meant like English.
Like a native English accent?
Yes.
Oh, okay. Then I have no idea. Maybe Australian.
Australian's pretty good.
I mean, Australians are hilarious. So.
Anyway, I don't know how that popped into my head. All right. Is it outro time?
Yeah, I think it might be.
Yeah.
Yeah, it's time to for me to go and figure out what we are going to eat. In you know.
Yeah, I have a virtual meetup with people. I have my usual Wednesday night gang, and we're gonna meet up virtually. So I'm gonna hop into reality.
That is.
But good night, sweet 203. It's been wonderful. Like, you know what I think this is like? Have you ever played the game Dark Souls?
I have not. Oh wait, no, I don't think I have.
So if you play it like online, people can like invade your it's like a single player game, but people can invade and like try to kill you as like a evil ghosty type person, and that's how I feel here. I feel like I'm invading a lecture to cause havoc.
Well, you certainly have done that. You've done your job. As John Boehner always said, the house has done its job. So
yeah. Love John Boehner.
I mean, God, no one even remembers that guy, do they?
maybe. I don't know.
Anyway, point is,
Anyway.
yeah, it's fun times. I think this might have optimized 203. This could have been the best 203 course, like the best section of 203 in the history of 203, right?
Well, you're talking about how great the students are, right?
Both. I mean, I think I'm gonna give myself an A plus. This was
really.
Yeah.
You're gonna give yourself an A plus.
A plus.
A plus.
A
You
plus.
know why? You know why? Because of the womp rats. That's what got you there.
Yeah, I think
It's
that
'cause
really.
you
I think
blasted.
that. I think that really made
You
it.
blasted so many. Every time I watch your videos, you're blasting womp rats, or you're pulling colorful balls out of sacks, boxes, bags, whatever.
Also, we definitely didn't accidentally break a lecture on the Monty Hall problem.
I think that was our finest hour.
Because so my problem was, I was thinking back to my recollection of working through it like a decade ago, and I thought to myself, yeah, no problem. And so
You know what? But by the end of it, you came up with the best explanation I've ever heard for it. So,
well, yeah, I mean,
birthed
I
something
kind of like reproduced not only Wikipedia, but then my own understanding of all the different explanations. I sort of pieced it back together eventually. But
yeah.
normally I wouldn't visit that kind of horror onto students where they have to.
Balls were in urns.
Yes, that. I mean, if you take a class and you do any kind of conditional probability and you don't talk about balls and urns, as strange as that is, yeah, we showed Monty what's for.
You, man, you need to do some more like video game loot tables, like drop tables. That's where you get your probability. That's where you know what? Actually, all the practical things I've used what I learned 203 for is like finding out how many times I need to schedule a dungeon run.
Yeah, I mean, really, that's Path of Exile stuff.
Oh yeah, that game as well.
But I mean, Path of Exile is like a lottery casino where you're like pulling the slot machine. It's like a slot machine. It's like a slot machine and probability, like conditional probability problem at the same time. But people think it's fun.
I liked Diablo.
Yeah, so you'd like PoE.
I like colors. Diablo has a lot of like sparkly explosions of things.
Oh, then you haven't seen PoE.
I played PoE back when it was new, and I was like, not for me.
Yeah, I like the game. They've added a lot to it since they've added more of the campaign stuff.
It's been out for like 10 years or something.
Oh yeah. Definitely.
We played the Warframe. Have you played Warframe?
Yeah, we played Warframe together for a few weeks.
Come a long way.
Yeah, I haven't played it in
Space Ninjas? Oh my gosh, you got a ninja through space.
Yeah, it's like
how it took people so long to combine space and ninjas.
Well, I mean, I think they were just running through the permutations of all cool things, right? It's like, ninjas, like...
I'm surprised they're not Space Ninja Pirates at this point.
Right, well, you see, that's... The probability of running into a three match like that is an order of magnitude lower than running into a 2 match.
Right.
So we just have to wait an order of magnitude longer time. So we estimate that it'll take approximately 100 years. Yeah.
Let's go get the video game development club that we have in the department, and you and I are going to be the product leads on Space Ninja Zombie Pirate game.
Space Ninja Zombie Pirate
game. Yeah. There's zombies, there's Space Ninja Pirates, and the Space Ninja Pirates are pirating in space, but there's also zombies around.
If you add in like... So basically it's like Doom.
It's like a zomboidal.
Yeah, it's like Doom in space, right? A little bit.
Doom in space?
A little bit. Because Doom is on Mars.
Yeah, Mars is in space. Everything's in space, technically.
Uh, yeah, I mean,
I think let's leave it that's it. I'm checking out. Everything's in space.
everything is in
We
space.
can't outdo that.
Well, I know we have a better outro, so we just have to wait a few seconds to get to the right outro.
Oh, okay. What's our better outro? Remember to like and subscribe.
I don't know.
Is space in space? Space is by definition in space.
Hang on.
Uh-oh. Did you get a different outro?
I wish I could take it all back. I honestly do. I honestly do wish I could take it all back. And not just because I'm stranded in space.
I'm in space.
I know you are, mate. Yeah, we're both in space. Anyway, you know, if I was ever to see her again, do you know what I'd say?
I'm in space.
I'd say, I'm sorry. Sincerely. I am sorry I was bossy and monstrous. And I am genuinely sorry.
I'm in space.
The end.
All right, guys. Later.
I